so far we use spectral method to solve diffusion equation, wave equation, and Burgers equation. Now we take up a more complex equation called Navier-Stokes equation. This equation is equation for the fluid flow. Okay, we have a fluid velocity field in a room, and I want to see how the velocity field changes with time. So here the velocity field U, velocity field is given by denoted by U symbol here, pressure by P, and there's a viscosity, so there's a friction, and that leads to this viscous term mu grad square U. Okay, and nu is called kinematic viscosity. Kinematic viscosity. So there's a density field as well, but we assume the flow to be having constant density like water. Density doesn't change much. So density is assumed to be constant, and which is not mentioned here. It's just a constant. Now it turns out for water, where density is approximately constant, we can this velocity field has certain constraint. So the divergence of U is 0. So del dot U is 0. So this is a condition on velocity field. Okay. Now this is called incompressible Navier-Stokes, NS, Navier-Stokes. Okay. So this evolution equation, velocity field is changing with time, and we solve using this equation under this constraint. So the constraint is del dot U 0. Okay. Now I'm going to only sketch. We will not write a Python code in this course for this problem, unless you're doing a project. But we just want to solve it. I just want to give you a sketch how to solve it. Okay. So we rewrite this equation in Fourier space. Okay. One difference between what we did in the past and now is that the velocity field is three-dimensional. Okay, unlike what we had in 1D, so it's just more complicated. So if I write the equation in Fourier space, I get this equation: d by dt of u hat k. K is a vector, which is a 3D vector, and I is a component. Now velocity is not only three-dimensional; it is also various components. So ux, y, uz. So I goes from 0 to 2 or 1 to 3, let's say 1 to 3. X, Y, Z. So I is equal to 1 is X, so I equal to 2 is Y, and I equal to 3 is Z. Okay. The nonlinear term, this term, it is more complicated. Now, if you know this notation, you write this is Uj, Uy, okay, and sum over J. So the u dot grad u can also be written in tensor form as this. So it means partial x, ux, uy, and ui. So it has many terms. In fact, it has 9 terms. So yeah. So here that's what we got. So partial j gives us ikj, and then we have uj full and ui, the real space. But I take full transform of the product. Okay, and compute that into a number k. The pressure term is gradient, so it's minus I k I p k, and the viscous term is minus mu k squared. Laplacian is minus k squared. So u hat k. Okay, so it looks pretty daunting, but if you follow the, if you just stare at it and you just analyze it, it's not very complicated. Okay, please remember that this sum over j. This is called Einstein notation. If any index is repeating, that means we need to sum it up. Now this is the nonlinear term, viscous term, and pressure term. So we write nonlinear term is n hat k, comma I for various components, Pressure is minus IKI PK and viscous term. I'm just rewriting that. Now the divergence term is given by Ki, U hat Ki. There's a square root of minus 1 outside, but it's a constant, so we can just pull it out. And this one is 0. Okay, so if you look at in Fourier space, this is a wave number K, then my velocity field is perpendicular. U hat is perpendicular. But we don't need it for this course. Now the nonlinear term is not computed by convolution. It is really a convolution, but we use Fourier transform to compute the nonlinear term. So we have U hat K in Fourier space. I go to real space by doing the inverse Fourier transform from here to there, then multiply various products, right? So in 3D we have UX, UI, then UX, UZ, and like that. There are 9 of them, but it turns out there's a symmetry. UX, UI is same as UI, UX. So you have basically 6. Okay, so multiply them, which is here, and then you do the forward transform. So you do the forward transform, then I get this. And how many terms? There are 6 of them, 6 terms, right? UI, UJ. And then I multiply by IKJ, and I get this. So it's a 3D multiplication. So please keep in mind that we have Kx, Ky, Kz, so it's a dot product 3D. Okay. So this is how we get the nonlinear term. Okay. And this is going to be order n cube log n cube instead of n power 6 in convolution. Okay. So a very similar idea. Burger's equation, if you know how to solve it, you can solve Navier-Stokes.